All right, Peak Speakers, this is video number 2. Now, when you all complain, oh, Peak, you better remember that I don't think any other teachers would do this for you. Okay, I'm done complaining. Hey, Peter Starbuck, have a seat, please. All right, so I am going to do conservation of momentum. Problem number 2. Okay, so the first thing that you have to remember in these problems is that momentum is mass times velocity. If you don't know that, you have bigger problems than this. Go back and do some more of your research and look at your notes. Momentum, we use a P for it because we're out of letters, equals mass times velocity. The other thing you have to know, total momentum before a collision must equal total momentum after a collision. Okay? You have to understand that those things are true. That is called the collision. There's one S, sorry. That is called the law of conservation of momentum. Just like the law of conservation of energy, momentum is not destroyed, it's not created. So if you have 10 objects that are going to collide, then you have to add up all of their momentum before, and that's going to be equal to all their momentum after. Okay? So I'm going to do example problem number 2. 2 children totaling 200 kilograms are traveling at 10 meters per second in a 100-kilogram bumper car during an amusement park ride. So I have 2 kids. La la la. Happy kids. And they have a mass, a total mass. This bumper car is 200 kilograms for the kids, total, plus 100 kilograms for the car. So I know that the mass is 300 kg. And it says in the problem that they are going 10 meters per second, so that is velocity. And they are going to collide with an empty car that has a mass of, let me look at the problem, 100 kilograms, and it is starting at rest. Okay? So these are the 2 objects before the collision, right? I've got 300 kilograms times 10 meters per second, and then 100 kilograms times 0 meters per second to find my total momentum. So the total momentum before my collision, this one is 300 times 10, because remember, P equals mv, okay, plus 100 times 0. My total momentum before is now shown. I know that that has to equal my total momentum after the collision. So I read the problem and it says, they deliberately collide, those evil kids, with an empty second car which is at rest. Afterwards, the car with the 2 children moves off at a speed of 4. What is the velocity of the empty car? So I know that the total has to equal the total after. So I have my 2 lovely evil children that are running into empty bumper cars. Their mass is still 300 kilograms, assuming one of them didn't barf. But now their velocity is 4, right? And then after I've got this empty car that's going to move off faster. Before it was at rest, but now this car has gone from 10 meters per second down to 4. That momentum, that energy has to go somewhere. It's going to go into the empty car. The empty car still has a mass of 100 kilograms, and the question asks, what is the final velocity of the empty car? So velocity is question mark meters per second. We don't know how fast it's going. We know it's moving because these guys bumped into them. So what I'm going to do is I'm going to find my before. 300 times 10 is 3,000, plus 100 times 0, 0, equals after 300 times 4, right, that's momentum, mass times velocity, plus 100 times the question mark. We don't know that velocity. That's what we're trying to find, okay? So that 300 times 4 is 1,200. So I know that 3,000, plus this over here, sorry, 100. I'm going to put a variable in for the question mark because I think it's silly to write question marks in my equations. So I'm going to write 100v, okay? So 3,000 equals 1,200 plus 100v. And v is just like x. So I'm trying to solve for v. I'm trying to figure out what it is. So the first thing I'm going to do is I'm going to get rid of this 1200 on this side. I'm going to do that by subtracting 1200. So I subtract 1200, and now I have 1800 equals 100V. 100 times something is 1800. What is V? Seems like I did some math wrong. Sorry, I'm checking my math. So 1800 divided by 100, how many times does 100 fit into 1800? It fits into it 18 times. So that means that the car is going to speed off, the empty one, at 18 meters per second. That's seeming a little high, but I think my math is correct. So this, of course, it's going to be greater because it's going to gain the momentum from this, right? This transfers the momentum to here because the total before and the total after must be the same. Okay? Now, the only difference you might run into on the sample problems is this is a completely elastic equation, meaning that this one goes off in a direction and this one goes off in a direction. If they're completely inelastic, then what you have to realize is that your masses combine after the collision. So if that confuses you and you're like, oh, Ms. Smith, I don't understand this inelastic, elastic, then just do an example like mine in your mini project. I'm sure there's another one on the list of an example. The golf club hitting the golf ball would be an example. If you want to challenge yourself, try the inelastic. And the difference is that these things stick together. So your after mass, I don't want to say a naughty word, I almost got a naughty word out with a tongue twister. Your after mass is going to combine, so it's going to be one, it's going to move like one object. And if you remember, there was that slingshot problem that we did, right, where the slingshot ran into the clay cube and they stuck together and went off into the sunset. So if you remember that problem, you can try one of those inelastic ones. Otherwise, stick with an elastic and then you know exactly how to do it because of this example. Okay? So hopefully that helps. Have an awesome day, and I will see you next week.